Two oppositely charged plates, A and B, are 0.01 meter apart. The uniform electric field between the plates is 4,000 newtons per coulomb, directed from plate B to plate A. A proton is released from rest at the high potential plate and accelerates to the low potential plate. A, determine the potential difference between the plates. B, which plate has the higher potential. And C, calculate the kinetic energy in electron volts of the proton when it reaches the low potential plate. There's a lot of subtlety that's in this problem. Let me start out with the fact that we know the direction of the electric field. They say it's directed from plate B to plate A. I'm going to sketch that in this diagram. I'm also going to recognize that if I put a proton, which is a positive charge, in this field, then it's going to be pushed from the right to the left. So the higher potential plate has got to be plate B. It's got to be the one that has the positive charge on it. I'm going to indicate the charge, and then I'm going to put the proton in there so that we can see what's happening. Now they tell me what the electric field is. 4,000 newtons per coulomb. Now, I think your authors are a little bit sneaky here, because the electric field could also be expressed in terms of volts per meter. If you don't believe me, you can work those units out. Newtons per coulomb is equal to volts per meter. Nevertheless, I know that there's a formula that relates for a parallel plate capacitor, this special case, the distance between the plates, d, which in this case is 0.01 meters, the electric field, and the difference in potential between the plates. Here's the equation. So I can find the difference in potential because I know what the electric field is and what the plate separation is. Plate separation is 0.01 meters. Let me throw in the numbers. I get that 4,000 newtons per coulomb times 0.01 meters is equal to 40 joules per coulomb. And a volt is the same thing as a joule per coulomb. So the difference in potential between the plates is 40 volts. We've answered part B. The high potential plate is plate B. C, we want to calculate the kinetic energy in electron volts of the proton when it reaches the low potential plate. Again, I think your authors are being a little bit sneaky here in the way that they've expressed this problem, because when we talk about electron volts, we're talking about energy. There is a conversion factor between joules and electron volts. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Now, that number looks suspiciously like the charge on the electron, except the units are in joules. It turns out that if you take 1 electron and multiply it by 1 volt, you get 1 electron volt. And that is that energy in joules. We're going to see electron volts are going to be very useful when we start talking about the photoelectric effect in the second semester. Now, I'm going to do this the easy way, and then I'm going to do it the harder way and show you that they're the same thing. The change in the kinetic energy is going to be the change in the electrical potential energy. And that change in the electrical potential energy is going to be Q, the charge of whatever it is that's being moved, times delta V, the difference in potential. We know what delta V is. It's 40 volts. Q is equal to the charge on the electron. Well, instead of writing it as 1.6 times 10 to the minus 19 coulombs, I'm going to write it as E. E being the elementary charge. 1 electron times 40 volts is equal to 40 electron volts. Electrons times volts. And the abbreviation for electron volts are EVs. That's the easy way to work it. Let me show you the more complicated way. Starting with our same equation, the change in the kinetic energy is Q delta V. Let me write the charge in terms of coulombs, and then the change in potential is still going to be 40 volts. Now let me throw the numbers into the calculator. So I get 6.4 times 10 to the minus 18 joules. But now let me use my conversion factor to make that into electron volts. And now I throw it into my calculator, and lo and behold, I get 40 electron volts again. There are several things that they didn't ask me in this problem that I would have to work in joules if I wanted to know. For instance, they might ask me, once the proton reaches plate A, how fast will it be moving? Well, in that case, I'm going to have to work in joules if I want my result in meters per second. And there will be some times when you have to do that, but in this particular problem, you don't. A plus 30 microcoulomb charge, which they call QL, is placed 30 centimeters from an identical plus 30 microcoulomb charge, QR. A. Determine the magnitude of the potential at a point P, which lies in a line between the two charges and is 10 centimeters from one of the charges. B. Determine the electric field at point P. C. Determine the work done by the electric field in moving a plus 50 microcoulomb test charge from point P to a midpoint M midway between the two charges. There's lots going on in this problem. First of all, let's take it step by step. And let's recognize that they're asking us for potentials in point charges. I'm going to use the principle of superposition to figure out what the total potential is at point P, and then I'm going to use these other relationships to help me solve the problem. Let's begin by writing down what the formula for the electric potential is for a point charge. Now in this case, I've got 2 point charges that are causing a potential at this point P. I've got a charge on the left and I've got a charge on the right. And I can figure out what the total potential is at point P by adding those 2 potentials together. In other words, the total potential at point P is going to be the potential at point P due to the left-hand charge plus the potential at point P due to the right-hand charge. Now, the potentials are going to be given by the formula for the point charge. Let me recognize that the distance from the left-hand point charge to P is 10 centimeters or 0.1 meters. And from the geometry in the diagram, the distance between the right-hand charge and point P is 20 centimeters or 0.2 meters. So now I can put these numbers in and figure out a total potential at point P due to the 2. Now I put the numbers into my calculator, and I get that the total potential at point P due to these 2 charges is 4.05 times 10 to the 6 volts. If you're not sure about those units, what you're going to see is, well, let me do one of those to show you where the units come from. I'm going to work on one of these. I'm going to work on the left-hand one. I see that I have a meters downstairs that can cancel a meters upstairs. And now I have a coulomb and a coulomb. They're going to cancel each other. And I'm left upstairs with newtons times meters, which is the same as joules. And then I'm left downstairs with a coulomb. And a joule per coulomb is the same as a volt. And that's what I've got. That's part A. Now, part B asks us about electric fields. And I want to draw your attention to the fact that the formula for electric potential looks very similar to the formula for an electric field for a point charge. And those 2 formulas look very similar to the Coulomb's law of force between 2 charges. The formulas look the same, but they're not the same. So be careful when you write these formulas down. Let me recognize that at point P, there's an electric field from the left-hand charge that would tend to push a positive chest charge to the right. So the direction of the electric field due to the left-hand charge at point P is to the right. The electric field due to the right-hand charge is to the left. The formula for electric field is KQ over R squared. Now, I can see that the electric field due to the left-hand charge is going to be stronger than the electric field due to the right-hand charge because the charges that are causing the field are equal in magnitude, but point P is closer to the left-hand charge. So the strength of the electric field is going to be more at point P due to the left-hand charge than to the right. So I could take the difference between the electric fields by those 2 charges. Here we go. So let me calculate what the magnitudes of those electric fields are. Let me throw in the numbers, and now let me insert them into my calculator. And I get that the answer is just over 2 times 10 to the 7th newtons per coulombs, and the direction is to the right. You could also say 2 times 10 to the 7th volts per meter. Either way, it's the same. Now, we've got to answer part C. We're asked to find the amount of work to move a charge from P to M. The fact of the matter is that the force that's acting on that charge is not going to be constant. So I can't use the simple work formula, work is equal to force times distance. I'm going to have to resort to something else. And the something else I'm going to resort to is to say that the work that's done is going to be equal to the change in the electrical potential energy. I'm going to recognize that this change in electrical potential energy is equal to Q times delta V, the difference in potential between points P and M. Well, I know what the potential at point P is. I found that in part A. If I could figure out what the potential at point M is, then I could figure out what the difference in potential is. And that's the way I'm going to approach this problem. So the change in the potential is going to be the final potential minus the initial potential. In the problem statement, they tell me what Q is. It's 0.50 microcoulombs, or 0.5 times 10 to the minus 6 coulombs. All that remains now is to figure out what the final potential is. What is the potential at point M? Because I know what the potential at point P is. It's 4.0 times 10 to the 6 volts. The potential at point M is going to be the potential due to the left-hand charge plus the potential due to the right-hand charge. I recognize that at point M, each of the two charges, the left-hand charge and the right-hand charge, are 0.15 meters away. So I can put the numbers in. Now we put the numbers into the calculator. So I find that the potential at point M, the final position, is 3.6 times 10 to the 6 volts. So now, let me put all that together to figure out what the work that's done is. I get the total work that's done is equal to negative 0.225 joules. Now what does that negative sign mean? Let me tell you, by the way, that I hate signs in these problems. So I tend to have to think about these things physically rather than try to depend on what the signs are. So here's the way that I think about it physically. First of all, I've drawn a diagram here that shows that where the charge begins at point P is a higher potential point. Where the charge ends at point M is a lower potential point. So that means that the charge moves from left to the right. The direction that the charge moves is to the right. Okay? Now the question asks us about the work done by the field. Well, which way is the direction of the electric field? The direction of the electric field is from high potential to low potential. So the direction of the electric field is also to the right, which means that the direction of the electric force is to the right. Now, while I can't compute numerically what the magnitude of the work is using the force times distance formula, I can say that if the direction that the charge moves and the direction of the force are in the same direction, then the work that's done by that force has to be positive. So in this case, the amount of work that's done by the electric field is a positive number, and it's going to be 0.225 joules. So now we've been through these 4 examples. You've seen electrical potential energy. You've seen a special case of electrical potentials for parallel plate capacitors, for point charges. You've been exposed to the idea of a ground, higher potential, lower potential, and now your head is swimming. I apologize for that. That's just the way that it goes. For right now, that's it.